Okay, all right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Let's get everything started here. Are your cameras on, or is it just me not seeing you guys? Okay. Well, I see Kevin. All right. Yeah, now you guys are popping up. All right. We sort of stopped right in the middle of something last time, so let's just jump right back into that. Let's see. Okay, so last time we started a new topic, officially starting calculus. We started talking about a topic called limits. And what is a limit, you might ask? Well, I told you last time. So we say the limit as x approaches a of a function is equal to a value L to mean that as x gets close to a, your y value will get close to L. Your output of your function will get close to L. And it does so in an unambiguous way. So everyone should be agreeing that, yeah, that's what the function is doing. So basically in this context, what we're looking at for a limit is we're looking for what is the y value getting close to as we manipulate our input. And so a limit is another way of tracking the y value. You can even think of it that way, right? As my input edges close to something, what's the y value doing, right? Whatever that answer is, that's what the limit is if it's unambiguous. Some important remarks to make sure that we're on the same page. So just remember that for the limit to exist, the function itself does not need to be defined. The function cannot exist at the point. There could be a hole, there could be something else going on. And you don't really need the function to work itself. Taking the limit is actually very different from just plugging in the x value and evaluating it, even though sometimes that seems to work. And it works in a very specific situation, which we're going to be describing later. So that's the second remark. So just to hammer that home, I actually put that remark twice. Limits do not care about what the value of the function is at x equals a. You do not care about what's going on at x equals a. You care about what happens as you get close to x equals a. And that's very, very important. Limits care about getting close to something, not necessarily being there. We also saw that limits may not exist. And there are two situations in which you can see that this will not happen. One is we spoke about the one-sided limits, limit coming from the left and from the right. If either of these don't exist or they are not equal to each other, the overall limit will not exist. And another situation in which a limit will not exist is if you can't get close. So we spoke about closeness in the context of limits meaning arbitrarily close. I should be able to get as close as I want. You'll notice here on the left, if I want to try to get close to a from the right side, there is no function up here to get close on, right? The function isn't even there, right? So my right-sided limit won't exist, right? Because I can't get close. There's no way to get close from the right. The limit cares about getting close. Sure, the function is filled in at a, but the limit doesn't care about that. It cares about as x gets close to a, what is the y value doing? However, from the right side, you cannot get close to a. You should be able to get as close as you want. So someone should be able to get to that point if they want. Someone should be able to get to this point if they want. You should be able to get as close as you want. So if you can't get as close as you want, the limit won't exist. In this situation here, whether you're coming from the right side or you're coming from the left side, you can't get close. So you'll realize that both one-sided limits don't exist, and therefore the overall limit does not exist, right? So limits care about getting close. You have to be able to get close to something in order to even make sense to even talk about the limit in the first place. So last time we looked at a bunch of examples about this guy, limit as x approaches 2 of 3x minus 1. We sort of saw that in this case, it seems like we could just plug in to get the answer, right? And yeah, you could technically do that because you could be at 2. That's super close to 2. So you'd realize that as x gets close to 2, this expression will get close to 5, right? That sort of makes sense. In our second example, this was not the case that we could plug in the number, but we realized that, well, other than at 2, this function behaves like the function x plus 2, which I can technically plug in 2 into that function, and the answer would be 4. And so, yeah, as x gets close to 2, this function will get close to 4, even though it will never actually be 4. It's never actually equal to 4. But we don't care about what the function is equal to. We don't care about whether we can plug in the x value or not. That's not what limits are about. We saw another example where we could actually take the limit from one side at a time, but we decided that based on our definition, this doesn't fulfill what a limit is about. So it introduced some ambiguity in there. So from one side, you're getting the outputs going to 0. From the other side, the outputs are getting close to 7. The fact that there's ambiguity there kind of messes up our idea. So in this case, we would say the limit does not exist. But of course, if limits are about tracking the y values, there should be some way to talk about this example, right? To say that, yeah, technically our limit doesn't exist, but I definitely can describe in detail what the y values are doing. I can describe what they're getting close to in certain situations. And so we invented what was called the one-sided limits, limit as the approach from the right and from the left. So from one side at a time, and then we could answer, we could give some sort of answer here that as we approach from the left side, the outputs are getting close to 0. If we approach from the right side, they're getting close to 7. Overall, the limit doesn't exist, but from one side at a time, we can talk about limits and they exist, right? So, and I also asked you to try this for next time. So we are eventually going to do that. But I just wanted to make some important remarks to make sure that I'm hammering, making sure, touching on important concepts again. Yeah, so this is again a restatement. Your limit will only exist if both one-sided limits exist and are equal. If either one-sided limit does not exist, or they both exist but they're not equal, then your overall limit will not exist. Limits seek to understand how the output behaves as you manipulate the input in terms of what it's getting close to. That's what you really want to get home, right? So it's not exactly the same as plugging in a value and evaluating the function, although there's a specific situation in which it can kind of seem like that, and it can actually be like that, and we'll talk about that later, actually. So let's learn some more about limits with those examples that I asked you guys to do, and it'll cause us to introduce some new concepts. So this is what I asked you to try yesterday. Let's actually get through them. So what did you guys get for this? Limit as x approaches 0 for 1 over x.
I got that the overall limit doesn't exist.
Okay, why?
Because when like x approaches 0, like because there's like the two different lines, like one approaches positive infinity, but the other approaches negative infinity.
So you're thinking about the graph. So this is definitely one of those situations where you can't plug in. But the trick that we used before on this guy, there was a guy where we couldn't plug in also over here, right? So we couldn't plug in the value over here. However, we could have simplified to get this thing. We could have simplified to get this thing, and that's sort of something that we can figure out what's going on with. However, in this situation, you should note that we don't have such an option. Like, how are you going to simplify that? Right? You can't really simplify anything. So we're not in the situation where we can do that trick. So what we can do is look at the graph. So the graph of 1 over x is a graph that I expect you to know by heart. It's like that. And now you can see as you're approaching 0, which is right here, if you get close to 0 from the right side, you're actually, you seem to be going up, up, up. So you can see that as x is approaching 0 from the right side, your y value is approaching, well, infinity, right? So we're going to introduce the concept of infinity here. I'm not going to get too formal about what that even means, but basically it just means it gets bigger than anything you can come up with, right? Whatever number you state, it's bigger than that, right? It's bigger than any real number. It just keeps getting bigger and bigger and bigger without bound. You can't stop it. It keeps growing. And so that idea is captured by infinity. Whereas on the other side, or is it use blue? Would yellow show up on the notepad? I don't know. On the other side, if we're approaching 0, then we're on this side of the function of here. And you'll notice that your corresponding y values are just getting smaller and smaller and smaller in the sense that they're getting more and more negative. So here we can see that as our x gets close to 0 from the left side, our y value gets closer and closer to negative infinity. Now, of course, the y value is never going to equal negative infinity because you can't be equal to negative infinity. But luckily for us, the limit doesn't care about being equal to anything. The limit cares about what are you getting close to. And this guy just gets closer to infinity in the sense that it keeps getting bigger and bigger and bigger, or smaller and smaller and smaller. And so we can describe it like that. So essentially what we can take away from that is that the limit as x approaches 0 from the right of this function is infinity. And the limit as x approaches 0 from the left of this function is negative infinity. And it turns out those two are not the same, which means the overall limit does not exist. And so that's the answer. Right. Limit does not exist because the left and right don't agree. So here I want you to realize that x is approaching 0 and 0, x is in the denominator. It's the only thing in the denominator. So here we are approaching division by 0. It's very important that you realize we're not actually dividing by 0. We're getting close to it, right? We're inching very close to it. And here it's like it doesn't even make sense. It doesn't make sense in the original function. It doesn't make sense for the limit. Division by 0 is a very weird thing. It's hard to overcome. So yeah, the answer here is does not exist. Then we had this example. Limit as x approaches 0 of 1 over x squared. Again, the denominator is approaching 0. We never actually get there, but it is x squared is going to get closer to 0. So for this one, did you also get does not exist? Because you can't divide by 0, right? What do you guys think about this one?
I got the limit is positive infinity.
Oh, how'd you get that?
Well, if you graph it from the left-hand side, because it's x squared, whatever negative x value you put, you get a positive y value. So left-hand side goes upwards.
Yeah. So this is the graph of 1 over x squared, which again is something that I expect you to know by heart. It's a very popular graph, I should say. And yeah, we can see that if 0 is the guy that we care about, the input is getting close to that, then yeah, if we approach from the left side, it goes up and up and up and up, right? We can't really describe that by a number, but we can describe that by a concept. So we can say as x approaches 0 from the left, our y value will approach positive infinity. And if we're coming from the other side, Then we're on the graph on this side. And again, we're going up and up and up and up. So we can say as x approaches 0 from the right side, our y value is going to approach infinity. Now, infinity is not really a number. However, you would be able to say here that, hey, both sides actually agree. We agree on what's going on. The y value is blowing up without bound. And so here, you'd be able to say the limit as x approaches 0 from the left of the function 1 over x squared is equal to positive infinity. And the limit as x approaches 0 from the right, again, you get positive infinity. And these are kind of, they're equal, asterisks, right? So these two infinities are equal, which is not always true, but we're not at the stage where we have to worry about that. Infinities can be different sizes, never worry about that right now. For us in calculus, we're always going to be talking about the same infinity. So that means because the two sides agree, the limit as x approaches 0 of 1 over x squared, we will say that it's equal to infinity. Now, can a function ever be equal to infinity? No, but the limit doesn't care about what a function can be equal to, right? It's what we're getting close to. We're approaching infinity. The values keep getting bigger and bigger and bigger, right? So the limit can be equal to infinity, even though the function itself can never be, because infinity is not a number. It's not a possible output. I do want you to appreciate here that the denominator of both of these expressions is approaching 0, but they behave very differently. One, we can say, well, it's kind of approaching infinity. One, we can say, it doesn't really do anything. Yeah, so division by 0 is not a thing. And even if you're getting close to dividing by 0, the answer can change. So there are people who believe, oh, you divide by 0, it goes off to infinity. Well, no, not always. For one, you can't divide by 0. And for a second, even if you're approaching division by 0, different things can happen. You don't have to get infinity as the answer. In fact, you can get any number as the answer. So even getting close to division by 0 gives varying results. In fact, you could also get any real number you want. I mean, it's kind of a silly thing to say, but here's an example. As x approaches 0 of that expression, the answer would be 5. And in fact, as x approaches 0, of any expression that looks like this, you would get n, where n is a real number. So you're getting close to dividing by 0 here because there's an x in the denominator, but it actually simplifies to just a regular number if you're not equal to 0, which the limit doesn't care. And so you can actually kind of technically get anything you want by getting close to division by 0. So it's not something, when you're getting close to dividing by 0, it is something that you have to approach very carefully. It can actually be done, not in Calculus 1 anyway. There are some different kind of mathematics out there where we do want to define division by 0 to be a specific thing, but in calculus, it's not a thing. It's never a thing. And it's never going to be a thing unless you're a math major where you really study some crazy things. So for us, division by zero is never a thing, and it gets kind of weird just by getting close to doing it. Here's another example. Limit as x approaches infinity, which is sort of interesting to think about, but intuitively it's what you think, right? So it means that the x value is getting larger and larger and larger without bound. You can't really stop it. It's just going to do what it do. So I don't like how that line looks. So here we're just looking as x goes to infinity. So we're just kind of getting bigger and bigger and bigger. We just keep going that way, right? So as x approaches infinity, right? So now remember, the limit cares about what is the y value getting close to. What is it getting close to?
0.
0. It's getting close to 0, right? As you're on this graph and you go over here and you track the y values, you realize that it's always going down. Does it ever hit 0? It'll never hit 0, right? Because it's 1 over x. Your numerator is 1. The only way a fraction can be 0 is if the numerator is 0. So we'll never actually hit 0 because 1 is not equal to 0, and it will never be equal to 0. So we can never actually reach 0. So 0 is just something that we're getting closer and closer to, which is what the limit cares about anyway. Notice that we never go down here because our graph is always above the x-axis. So we're always going to be slightly positive, but we're getting closer and closer to 0 as opposed to some other positive number. If you were to tell me any other positive number, eventually I'll get smaller than that. And so 0 is the only thing that could be the answer. And so, yeah. So there is the concept of the input getting huge without bound. And you could also have the input going off to negative infinity. Now, it does not mean that you can actually plug in this value, but again, the limit doesn't care about plugging in the value. The limit cares about approaching something. And you can approach infinity, right? Even though you'll never be equal to it. The limit doesn't care that you can't be equal to it. So that introduces some new concepts for us. And I think I do mention that here. Right. So in case you weren't aware, yes, infinity and negative infinity are valid answers to what a limit can be equal to, right? And yes, there are also valid possibilities for a in the expression limit as x approaches a of f of x, right? We can let our x approach positive infinity or negative infinity, and the answer to what the limit is could also be positive infinity or negative infinity. And we have names that we give to these things. So when we're looking at this limit, if your a is approaching positive or negative infinity, that is your input. We say you're taking a limit at infinity, right? So if the input is going off to infinity, we say you're doing a limit at infinity. You're at the x value infinity. If your output of your limit is infinite, either plus or minus, then we say you have an infinite limit, right? The limit is infinite, right? The y value is infinite. It can be both, right? So for example, if I were to say the limit as x approaches infinity of e to the x equals infinity, that is both an infinite limit because the answer is infinity, but is also a limit at infinity because your x is approaching infinity. So it's an infinite limit at infinity, which is a mouthful, but it's just talking about the output versus the input. And it's just what we call it. just so you know. Yeah. So yeah, infinity can come into the mix, even though it's not in the mix for regular functions, because functions can be equal to infinity, but limits don't care about being equal to anything anyway. So this is one way in which they can also differ from being able to plug in and get a real number output. Okay, so going over those would introduce those new concepts, which we're going to be using soon. So now, the examples that we've been doing, I've been showing you on graphs and we've been discussing them. And I really wanted you to get an intuitive idea of what a limit is. But at the end of the day, it's Calc 1. I'm going to give you a test. I'm going to ask you to do a bunch of limits. I don't expect you to be all fuzzy about it. I want you to be very efficient and able to compute limits very quickly. So what we're going to do now is talk about a strategy for computing limits. Okay. So there's going to come a point where I'm going to give you a bunch of random limits to do, and you're going to have to be able to do all of them in relatively a short amount of time. So to that end, I'm going to give you a general strategy for approaching limits, right? You see a random limit show up on a test or a quiz or wherever. How do you actually approach it? What do you do? Do you always have to draw a graph? What if the thing is complicated and you don't know what the graph looks like? I'm going to give you some general tips that will help you compute limits. That should help you deal with any limit I can give you, at least in Calc 1. And in Calc 2 as well, by the way. But yeah, so that's what we're going to do. So general strategy for computing limits. And I want you to think of this strategy as not just options, but as directions, in the sense that you should do step 1 before step 2, before step 3. You kind of think in this order, right? So it kind of builds on like easiest to harder things to do. And so if you can do something easy and get away with it, you should just do the easy thing and get away with it. You only move to harder things if you really have to, right? So that's just a general kind of efficiency sort of thing. If you can do something a hard way and an easy way, the hard way is going to take more time and effort. Like, why would you do it that way? Do it the easier way, right? So that's what the strategy is going to do. It's going to help you to compute random limits, but also compute it in a very efficient way, right? So yeah, you want to compute a random limit. You have some random guy like this, limit as x approaches a of f of x, and you want to know, what is that equal to? What do? Well, the first thing you do, which is going to seem to fly in the face of what I've been saying, is try to plug in the x value, right? Now, I know I already said taking a limit is different from plugging in the x value, and it is. But in almost every circumstance where you can plug in an x value, I should state that differently. In almost every circumstance in Calculus 1 where you can plug in the x value, then the limit will actually give you the same value as plugging in the x value. They will happen to coincide. It's not that they're the same thing, but they will happen to give you the same answer. And so if you can plug in the x value, chances are you should do that. I should also state that it does not apply to piecewise functions for sure, because you can plug in a value when coming from one side, but the other side can give you something different. So if you just have a function that at the point it's not doing something crazy different on either side, you can get as close as possible from either side, and the value actually exists there, then you can plug in the value to compute the limit. This is done more generally. It's you can do this whenever a function is continuous, quote unquote. We haven't spoken about what that is yet, but we will soon. So for the most part, if your function is continuous, the limit will give you the same value as you plugging in the x value. And in Calculus 1, if I give you a random function, it's not a piecewise function, chances are it's going to be continuous at the value that you can plug in x. So that would be a thing. So that's step 1. To do an example of step 1, we've seen an example where step 1 can work, right? So an example was oh, what was the limit as x approaches 2 of 3x minus 1? And we saw that the answer was 5. I could literally just plug in the limit. And 5 would be the answer. And that is because is continuous at x equals 2. Therefore, the limit and me evaluating the function will agree at x equals 2. Continuity, or what it means for a function to be continuous, like I said, we'll deal with that in detail later. But intuitively, it just means you can draw the function without lifting your pencil off the page, passing through x equals 2. There's no disruption, there's no hole, no gap, no breaks, nothing. Like it's very smooth going through 2. And because you can do that, you can just smoothly draw a line going through 2, moving on the graph of the function. You can plug in, and that would give you the answer. And that's it. You don't have to draw the function. You can realize, oh, I'm able to plug in 2, and it's just a straight line. It's very nice everywhere. It's not, there are no disruptions I have to worry about. I can just plug in the number, and that would be the answer. Right? So that's the first thing. If you can plug in the number, plug in the number. Right? And as long as both sides agree and there's no gap, no disruption, that's what you do. You can get away with it pretty easily. All right. Second step, right? So remember, the steps go in order. So you only go to step 2 if you know that step 1 is not going to work, right? So you don't jump to step 2, you try step 1 first. If you can plug in the number, just plug in the number. Step 2, what if you can't plug in the number? Then you're going to try to simplify so that you can plug in the number, right? So here's where your algebra skills, right? So need algebra skills here. Right? So one, having good algebra skills is going to make you realize that this thing is simplifiable in the first place. Like I'm not going to waste my time trying to simplify it, and it can't simplify it. So good algebra skills will help you to know that. And 2, good algebra skills is going to actually, you're going to have the skill to actually simplify it when you know that it can be simplified. So you'll be able to factor and cancel stuff, or multiply and divide by conjugates, or do something like that. So that's what's going to happen. And of course, we saw an example where this would work. So we had the limit as x approaches 2 of x squared minus 4 over x minus 2. So notice the first thing I would think here is, can I plug in x equals 2? And the answer was no. Nah, dude, you can't do that because that's division by 0. You do that, Jhevon kills you, right? So then you ask, can I simplify? Right? And that's when your algebra skills kick in and you're going to be like, oh, x squared minus 4, that's a difference of squares, right? I've seen that 1,000 times at this point. I can do something here. So that's what brings you to this step where you say, okay, so that's going to be, I'm going to can factor that as x minus 2, x plus 2. And then these guys can cancel because I'm canceling cross multiplication. So this is actually going to be equal to, as if it's going to give me the same value as if I were taking the limit of just the x plus 2. Now I cannot be equal to 2, but the limit doesn't care about being equal. As long as I'm not at 2, this thing is going to behave like x plus 2. And so now I'm in a situation where step 1 applies. I'm looking at a limit where I can just plug in the number. I can plug in 2 into x plus 2, and that will make a valid answer. And so the answer here is actually 4. Now there's something else I want you to notice here. I want you to notice I keep writing the limit symbol, limit as x approaches 2, until I take the limit. So notice that I kept rewriting the limit sign until I actually evaluated, right? So the limit sign, it sticks around. So while I'm simplifying, the limit sign is there because I didn't actually compute the limit yet. I'm just simplifying to get to a point where I can compute the limit. So I keep writing the limit symbol until I get to a point where I can actually give you an answer. So notice that the limit symbol disappears once I actually get to a point. It disappears once I'm actually at the point where I can actually compute stuff and give you an answer. Right, so you have to keep writing the limit sign. And that's important. That is something that I would deduct a point if you don't do. So just giving you a fair warning. I know it seems mean, but paying attention to notation is actually super important, as I said. You'll be surprised how much misery and mistakes that students could avoid if they simply just paid attention to how they were writing things down. So yeah, you keep writing the limit symbol until you can actually evaluate the limit. So that's step 2. So you see a random limit, what are you going to do? First, try to plug in the x value. If it works, awesome, that's your answer. If it doesn't, try to simplify so that you can plug in the x value. And it's possible for that to work, but it's also possible that it doesn't. The examples up here was a situation where it doesn't, right? Here, I couldn't plug in x equals 0. Can I simplify to plug in 0? No, I couldn't simplify either. So now I had to do something else. I had to think about the graph. Oh, well, I know for this, right? I had to do something else here. But these first 2 steps is what you're always going to do. The third step is something I'm going to mention at this point and move on, but is to apply a special technique. If you're in the situation to apply a special technique, you should apply that special technique. And the thing is, I haven't really told you about any special techniques yet, but we're going to discover some today. So stay tuned. We'll learn some special techniques pretty soon. So yeah, sometimes you can't really plug in a number, but you can apply some sort of special technique, right? So you can get away with it based on what the function actually looks like. Yeah, so nothing to say about that actually right now, so I can actually put the space back. Okay, step 4 is to use your knowledge about how different functions behave in relation to each other. This is especially useful when you're taking limits at infinity. So if your input is going to infinity, this is actually super helpful. So I told you guys last time and the time before that, I think, that this relationship about exponentials growing faster than polynomials, growing faster than logarithms when your base is larger than 1. And in the sense that guys on the right, as x is going off to infinity, they become so huge compared to anyone on the left, so that anyone on the left might as well be 0. You can essentially think about them as if you're thinking about 0. They don't matter, right? So if you have an exponential competing with a polynomial and your x value is going off to infinity, it's an increasing exponential, it will always beat any polynomial. If you have an increasing polynomial and you're comparing it to a logarithm, it will beat any logarithm. the polynomial will always win against a logarithm, an exponential will always win against a power function or a polynomial. So just you knowing about how different functions behave in relation to each other can be super helpful. It's also worth mentioning that for the power function and exponential category specifically, the same is true within a category. So for example, x to the a is going to be much smaller than x to the b if your b is greater than a. So for example, if you're comparing an x cubed to an x squared, eventually x cubed is going to get so huge that your x squared might as well be 0, might as well not even try. And similarly for exponentials, if you are comparing, say, 3 raised to the x compared to 2 raised to the x, eventually 3 raised to the x is going to be so huge that 2 raised to the x might as well be 0, might as well not even try, right? So when you're going off to infinity, some functions really overpower other functions, and knowing about that can be very useful. So I'll give you a couple examples of that situation. So example. If I'm looking at, say, limit as x approaches infinity of e to the x over 2 plus x minus or plus x to the 1000, right? You see a random limit like that. First thing you would do, can I plug in the x value? Dude, the x value is infinity. You can't plug it in. All right. Can I simplify so I can plug in the x value? Dude, the x value is infinity. You can't plug in. And how are you going to simplify that thing anyway? All right. So first 2 steps don't work. So now, special technique, don't worry about that because I haven't taught you any yet. So now you get to this point where, all right, I see that there are 2 different kinds of functions in this limit. There's an exponential in the top, and then there's a polynomial in the bottom. Now, I know about the behavior of functions. I know that exponentials win against polynomials whenever the base is larger than 1, which means the e to the x here is going to win against any polynomial. So in fact, the denominator compared to the numerator is tiny, might as well be approaching 0. And the e to the x is getting huge. We know what that graph looks like. And so this is going to be, well, infinity. Right? You can know what the answer is. I don't have to graph it, don't have to do any calculations. I could do infinity, and I could say something like, this is top heavy. Right? And as far as I'm concerned, that's showing your work, right? Just tell me, oh, the answer is infinity because it's top heavy. The top gets much heavier than the bottom, so it gets huge, and it goes off to infinity. So that's just me knowing about that. Or I can look at another example. Limit as x goes to infinity of x squared plus 2x plus 1 over ln of x, right? And here, it's a polynomial versus a logarithm. And the polynomial wins. In fact, let me actually, I want to do that the other way, just to give you a different answer. Ln x divided by the polynomial. In this case, the denominator is a polynomial, the top is a logarithm. Polynomial wins, right? As we're going off to infinity, right? So because we're going off to infinity, I know how these functions relate to each other. The polynomial is going to win. So the numerator might as well be 0, and the denominator is getting huge, which means you get 0 as the answer. And that's what happens when you're bottom heavy. Okay. So you can just say, I know the limit is going to be 0 here because it's bottom heavy. The bottom outweighs the top. So you have a fraction where the top is super small and the denominator, the bottom, is super huge. That gets close to 0, right? You have a fraction where the denominator is very big compared to the numerator. That fraction is going to be close to 0. It keeps getting smaller, right? Think about 1 over 10 versus 1 over 100 versus 1 over 1,000 versus 1 over 1,000,000. The bigger the denominator gets, the smaller the fraction gets. so it's going to approach 0 because they're both kind of positive. And so that's bottom heavy. So you can actually use different functions to relate to each other. Just to know about the relationships, know about the behaviors, you can get a lot of information about that. And particularly when you're approaching infinity, these relationships that I gave you here is very useful to know that exponentials beat polynomials, polynomials beat logarithms. These two guys over here, we're definitely not going to talk about this guy, X. Well, I'm kidding. It's not, the exclamation is read factorial. It doesn't mean you're shouting. X factorial, it's a different kind of function. You'll see that in Calc 2 for those of you who are going in Calc 2. X to the X is like an exponential with the base also being a variable. That guy also grows huge, and they're bigger than all the other guys we've spoken about. And so X factorial, we're definitely not going to see, but X to the X, we will be seeing things like that in this class. But just know that if they show up in a limit, this guy is pretty much going to be bigger than anything else, any other function that you're going to come up against as X goes off to infinity. Yeah, so just knowing how these guys relate to each other. And just knowing, as I mentioned, within each category for the exponential. So like if I have 3 to the X plus 1 over 2 to the X plus 5,000, this still goes off to infinity because it's top heavy. Right? So because 3 to the X compared to 2 to the X, the base is larger. So that is true. Okay, so that's a strategy, step 4, right? So if all the previous things didn't work, maybe you can figure something out based on the actual functions involved, right? And especially if you're going off to infinity, you can actually use that idea. The fifth thing is to do what we did earlier, is just know about the graphs. Graphs or a table of values can work here. I can do another thing here too. Just to show you that polynomials can work. If I have 5x to the 5th plus 3x minus 1 over 2x squared minus 3x plus 17, that's going to go off to infinity, top heavy. There are some things to worry about top heavy functions, but I'll actually get to that soon, because you could get a plus or a minus infinity, and I want you to know that you have to look out for that and know when you'd get which. But also, the guys that we saw earlier apply. So if I'm looking at something like that, you should know that that would be 0, not even from the graph, but because you know that this is bottom heavy, because the numerator is a 0 degree polynomial, while the denominator is a 1st degree. Right? And based on what I said above, we know that x to the 0 must be very much smaller than x to the 1, because this rule that I have here. So you didn't even have to draw the graph for this. You can actually know that, oh, the answer is 0 because it's bottom heavy. The polynomial on the bottom is much bigger than the one on the top. It's going to go off to 0. You have a fraction where the top might as well be 0 compared to the bottom as you're going off to infinity. So step 5 is to use the graph of a function or a table of values. Now, graphs are sometimes useful. Table of values, not so much, because in this class, in theory, you're not supposed to be using a calculator on any of the exams. And so to compute stuff by hand is just kind of, right, even though technically you could do it, it's going to be much harder than you would want to do it. But you can do the graphs. So example, we saw examples like this already. So as x approaches 0, if 1 over x squared equals infinity, since we know the graph looks like this. Right. As we get closer to 0 from either side, the graph goes up. So as x gets close to 0, y gets close to infinity. And so I can just know, oh, the graph, right? For this particular function, it also works to just know that, oh, the bottom is a second degree polynomial, the top is a 0 degree polynomial. But this kind of works as the inverse relationship because we're approaching 0 as opposed to infinity. But yeah. Yeah, you could do that. Versus the same thing, we can know that this guy, x approaches 0 if 1 over x, does not exist, since I can look at the graph and realize that if I approach 0 from this side, it goes up. If I approach 0 from this side, it goes down. So left and right don't agree. Let me show you what the table of values might look like. So let's say I wanted to do limit as x is approaching 0 of 1 over x, right? And I want to know what that is. And for whatever reason, I just don't believe in graphing stuff, right? So I'm going to start to plug in numbers, right? So what would that mean? So what I can do here is track the x and the y. Now, obviously, there's a line in here where it's going to be 0, but I don't know what the y is behaving like. So what I can do is I can use a table to do what I know the limit would do anyway and get closer and closer to 0. So I can start at something like 0.1, 0.01, 0.001, 0.0001, right? Notice I'm just plugging in a bunch of random values that they're getting closer and closer to 0, but from the right side. Now, if I take 0.1 and I put 1 over 0.1, 1 over x, right? 0.1 is like 1/10, right? And this was 1/100th. And this is 1/1000th. And this is 1 over 10,000, right? So if I flip those, this guy's going to be 10. That guy's going to be 100. That guy's going to be 1,000. This guy's going to be 10,000. Clearly, you can see as I'm coming from this direction, I'm going off to infinity. We get larger and larger. Right? And so now you might see, okay, what are we doing from the other side? So here, you're on the other side of 0, which means now you're negative. So you can plug in something like negative 0.1, negative 0.01, negative 0.001, negative 0.0001. And you'll notice that the opposite happens over here. You'll have negative 10, negative 100, negative 1,000, negative 10,000. You'll notice that as you're approaching from this side, you're going off to negative infinity. So we get more and more negative, right? And so then you can look at these two and be like, they don't agree. So that tells you the limit does not exist. I'm going to do some more examples eventually. Right? So I can just plug in values, see what's going on with the outputs, because the limit, after all, is trying to track the output, right? I want to know as my x gets close to 0, what are the y values doing? What are they getting close to? And so I could do this via a table of values. Similarly, I could have done, what is the limit as x approaches 0 of 1 over x squared? Don't know what that's equal to. For some reason, I don't want to use the graph or the fact that I know that the bottom polynomial beats the top polynomial. I can just, again, do a table of values. So 0 I care about, but I don't know what the y value is doing there, or what it's even getting close to. So I can do the same thing, plug in 0.1, 0.01, 0.001, 0.0001, minus 0.1, minus 0.01, minus 0.001, minus 0.0001. And so this guy's 1 over x squared. So it's 1 over 1/10 squared, which is 100. So this is actually going to be 100. This is going to be 10,000. This is going to be a million. Yeah, that should be 4 zeros, should be 6 zeros, should be 8 zeros. Right, so clearly this side, we're going to infinity. Now, because it's a square, the negatives are going to turn to positives. So I'm actually going to get the same sort of numbers here. So from this side, I'm also going to infinity. And then I see that, oh, they agree. And that tells me that the limit does exist, and I'll call it infinity. Right? And you can do table of values, and you'll realize that if you do table of values with any of the examples we've done so far, you'll actually get close to what the actual answer is. So if you look at something like limit as x approaches 2 of 3x minus 1, you can plug in 2.1, 2.01, 2.001, 2.0001. And then you can go and you can plug in 1.9, 1.99, 1.9999, 1.99999, right? And then you'll realize that the answers, when you compute the output, they get closer and closer to 5. You'll realize the answers are something like 4.9, 4.99, 4.999, 9999, right? And you'll realize that's happening from both sides. And you'll be like, that's getting closer to 5, right? And you can tell that from the table of values. Now, generally, of course, that is going to be really annoying to do by hand, right? This is a super easy thing to plug stuff into. So generally, I would not recommend this, but it's a valid option technically. But if you're going to do something like this, I mean, I would just, the graph would probably be nicer. So that would be like step 5. Yeah. So, and that's it, 5 steps. Knowing these 5 steps and applying them, you can conquer any limit. Now, of course, there's a bunch of stuff in step 3 that I haven't really spoken about yet, but we will. But generally, this is the strategy for approaching any limit and computing any limit. First, try to plug in the value. If it works, great. If it doesn't, move to step 2. Can I simplify so I can plug in the value? If that works, awesome. If it doesn't, move to step 3. Does this look like something I can use a special technique on? Okay, when Jhevon teaches me these special techniques, I'm going to use it. All right, if that doesn't work, step 4. Maybe just looking at the kind of functions that are there, I can tell something. Is it like an exponential and polynomials? Or is it like a logarithm and an exponential? And I can talk about, oh, this guy's going to be bigger than that guy, so I know this is going to happen. Or 5, you can use, what do I know about the graph? What would I know if I plug in values? And you can do that, and that can get you to the answer. So yeah, those are the limit strategies. So step 1, the plugging in idea, really that works when a function is continuous. But chances are, if I give it to you and it's not a piecewise function, you're going to have that being true anyway. So it's almost safe to say that you should try to do this, but technically you can only do this when the function is continuous. All right. Do some more examples. Let's put the strategies to the test. Let's just make sure that we know how to do the strategies. Right? So I give you all these random limits here. We are going to do them based on the strategies. Creating some space here. Yeah, try to plug in values into that guy, right? Have fun. Then you're going to be like, man, Jhevon, that test was so long. I spent like half an hour on problem 1. Jhevon sucks. His tests are hard. He's a GPA killer. Yeah. Yeah. Sometimes it's like we're living in different universes. Like, yeah, that was one way you could do the problem, but that's like 30 minutes longer than the way I expected you to do the problem. So I was thinking of that this way when I wrote the test, not that way. Yeah. All right. Here's a limit. Limit as x approaches -1 of 2x minus 3 over x to the 4th plus 1. What is the answer? Remember, you're training grasshoppers. Oh, let me do done. Let me give you guys the notes again so you can have the strategies up in another window or something. Because you should be referring to them for everything. Okay, so I posted the link to the notes. You can open it and like just have it set on the strategies in like a window somewhere that you can minimize like on half the screen. All right, what do we think? Anyone? Bueller? if anyone got that reference. Probably not. You'll be like, what's wrong with this guy? Jhevon's just randomly saying words. Is something wrong with him?
I actually like looked in the participants list to see if you were like cold calling. I was like, who's Bueller? Where's Bueller?
Yeah, you're looking. Yeah.
Yeah, that went over my head. But is it -5 halves?
Yeah. There's a cult classic movie called Ferris Bueller's Day Off or Day Out or something like that.
Yeah.
Where it's like this kid who plays hooky from school and his teacher is just calling his name and no one's answering, but the teacher keeps calling the name. Bueller, Bueller, Bueller. And like no one's answering, but he keeps calling the name. So yeah, that's where it's from. Old people would get the reference, but you guys. Yeah, so here, what did you do?
I plugged in. I know I probably wasn't supposed to, but
Plug in, why not? What's the problem? Would the denominator be 0?
no.
No, so we can plug in, right?
Okay.
Yeah, you plug in, step 1. So that's -2 minus 3 over 1 plus 1. It's -5 over 2. Yeah, step 1. Cool, all right. So starting off easy, let's see. This one. What do we do here?
I got 1/6.
How did you do it? What did you do?
I simplified I factored out the bottom, so then it was like x plus 3, x minus 3, and then I got 1 over x plus 3, and then I plugged in 3 and got 1 over 6.
The bottom is what?
X 3
It's not x plus 3.
okay. It's 3
3 minus x,
minus
3
x
plus x, yeah.
x.
All right. And so what is that? Okay, simplify now. Are we stuck? What do we do?
Doesn't x minus 3 and 3 minus x technically cancel out and become a -1?
Right, you can get a -1, right? Tons of ways you can see that. You can see that this would cancel into that -1 times. One way you can see that to like just factor out a negative to turn things around. Then those guys would cancel. You would end up with the limit as x approaches 3 of -1 divided by 3 plus x. And now I can plug in x equals 3 because it's not division by 0. Nothing weird is going on. It's just somewhere where it's nice. I can plug in this and get a value. Why not? So it's -1/6. Let me make it clear what I was doing here. Yeah, so here I couldn't plug in because obviously if I plug 3 into x here, the denominator would be 0. And Jhevon will kill you if you divide by 0. So you move on, you try to simplify. And you could simplify here, and you got to a point where you could plug in the number. So this is like step 2. And notice that I keep writing the limit sign until I actually can do something to figure out what the limit is. Okay, what about this one? What strategy do you think works here? What would you do in this case? Are you saying something, Makai? Because I can't hear you, but I saw you on mute. What do you guys think we should do? Simplify the bottom, all right. That's again a difference of squares. Seems like the right thing. Of course, we'd first think, oh, plug in the number, but I can't plug in x equals 3 because that would make the denominator 0. All right, so I can cancel that. Nice. All right, so now we move on. All right, so what do we do now? What's the answer? So we can't plug in. So simplify. And then you get here and you're like, ah, still can't plug in. At this point, you're like, man, Jhevon never told us how to do it. Jhevon doesn't teach us anything, man. You just get the examples in class are so hard and easy, and then he gives us this, and he told me that if I simplify, I can plug in, and I can't plug it. Well, no, right? Once you simplify, the process starts all over. Now you pretend like this is the limit that you were given, and you go through the process over again, right? So now, if we pretend that that was the limit that we were given, what would we have done? We would try to plug in, but we can't. So now what we can do, try to simplify it so we can plug in. We can't simplify. We've already simplified as much as it can simplify. So it means that step 1 and step 2 doesn't work. That's all that means, which means you need to go down the list. What is another strategy you could do? So for this particular function, what do you guys think you can do?
Would it be easier to make a table?
Sure. What would you do in the table?
I would plug in 4, 3.1, and 2.9. I mean, just 2.9, not 4. Never mind, just 2.9.
Is that good enough? Because you'd have to approach from both sides, right? And and the idea is with a table, you have to plug in a bunch of stuff. Now, there's one way you can kind of show me that you're thinking about plugging into a table, even though you're not plugging into a table. So that would be something like realize here. But if we look at what would happen as we approach 3 from the left of this guy versus approaching 3 from the right of this guy. So approaching 3 from the left, right? So that means you're on the left side of 3. So this is where you're like 2.9, 2.99, 2.99999, right? So if you do that, so we're plugging into this x 2.9, 2.99, 2.999, 2.999, but I'm not going to worry about the specific value because ain't nobody got time for that, right? So what can I know is happening? Well, the numerator is staying at 1 and the denominator is getting close to something. What would it get close to? The closer x gets to 3, the closer it gets to 0, right? Now, the thing is, I'm never actually going to get to 0 because I can't. And 2, the limit doesn't even care about that anyway. So how I can express that is to say, well, I'm getting close to 0, but with a slight negative charge, right? So I can say here, getting close to 0, but we are slightly negative. Right, your denominator is going to get smaller and smaller and smaller the more you plug in like 2.9, 2.999, 2.999, 2.99999. But whatever you're doing, if you're plugging in a value that's on the left side of 3 on the number line, if you take that number minus 3, you're always going to get a negative number. Now, conversely, if you're on the right side of 3, so you're plugging in 3.1, 3.001, 3.0001, 3.0001, one thing is that's going to be true is that your x is always going to be slightly bigger than 3. So this is going to be 0 with a little positive charge. Okay. Now, what that tells you is that it's going to behave like 1 over x, right? Where x is going to 0, but from the negative side over here. So this guy is going to give you a negative infinity. Not because dividing by 0 gives you negative infinity, because we're not dividing by 0. We're always slightly negative. Whereas over here, you would get positive infinity. Now, the fact that those two don't agree is what's going to tell you that the limit as x approaches 3 of 1 over x minus 3 does not exist. And that's going to be your answer. There's no answer here. It does not exist. That's one way. Of course, another way is to use the graph because 1 over x minus 3 is not a difficult thing to graph, or it shouldn't be if you know your pre-calc. Y equals 1 over x minus 3 is just like the graph of 1 over x, but it's shifted 3 units to the right. So the graph is going to look like that. And you'll see that if you're coming from the left side, you're going down. If you're coming from the right side, you're going up. These two don't agree. So limit does not exist. So yeah, if your thing doesn't work, you just keep going down the list, right? So here, step 1 can't work here. So we did step 2. And we ended up in a situation where we couldn't finish the problem. So you just move down, step 3, step 4, step 5. You keep going down the list. You're not going to get through to step 5 and not be able to solve the problem. Like this list that I gave you is exhaustive, other than the fact that I haven't really told you anything in step 3 yet. But once I tell you all the stuff for step 3, this process will solve any limit you will encounter in calculus 1, right? You're not going to get to the end without being able to solve the problem, assuming you have the algebra skills and all that to pull it off. So if you try something and it doesn't work, just keep going. Just move to the next step. Yeah, so that's what happened here. We had to keep going. So this pretty much here, we ended up with like step 5 here. Right? We had to go through like 4 steps before we could get to anything useful. Yeah, you just keep going down. So that's a nice little clever way to kind of show me that you're thinking of table of values without actually writing out the values. You can just know, well, this is going to get close to this number, but slightly bigger than it. And this is going to get close to that number, but slightly smaller than that. And so this fraction is going to get closer and closer to this thing. But yeah, of course, you'd have to have good number sense to be able to reason like that as well. But the graph here is pretty easy to draw. So I would say that it's okay to do that. All right, this example. Try to plug in, can't plug in, right? So what do we do? Try to simplify. How would we simplify this? So here you'll notice can't plug in. So you might ask yourself, can I simplify? Can you? We did talk about this in the first class, so maybe I could just recall. What does absolute value of x mean, right? If we're going to simplify it, we need to know what it means. Remember what we said it was? So absolute value of x was a piecewise function. It's x if your x is positive, it's minus x if your x is negative, and 0 if your x is 0. Right? So we can apply that here. It's going to be the limit as x approaches 0 of x over x in the event that your x is positive. So you're really just approaching from the right. And it will be the limit as x approaches 0 of minus x over x if your x is negative from the left. Now, what is it if x equals 0? Well, it's nothing because you can't divide by 0. And limit don't care anyway. It's like a honey badger. I don't care about being at 0. Irrelevant, completely irrelevant. However, I know if I'm on the right side of 0, my absolute value of x is going to just evaluate to x. If I'm on the left side of 0, my absolute value of x is going to evaluate to negative of x. so that I take the negative of a negative to make it positive. The absolute value always wants to turn everything positive. Whenever it's negative, it'll just multiply by a -1 to turn it positive. So this guy ends up looking like well, now you just think of each of these limits individually and start the process over again. So try to plug in, can't plug in, divide by 0. Can I simplify the plug-in? Sure. X over x cancels, right? That cancels into 1. And what about if it's less than 0? Well, it cancels into -1. So now you would realize that, well, what is the limit as x approaches 0 for 1? Well, you have a function that's y equals 1. As x gets close to 0, what is it going to be equal to? Well, 1. It's always 1. It's a constant function. Limit of a constant is always going to be just a constant. So that's going to be 1 in the event that your x is greater than 0. And it's going to be -1 in the event that your x is less than 0. Now, we are looking at the limit as we approach 0. So what does this tell you about the limit?
It doesn't exist.
Does not exist. Left and right don't agree. So in a weird way, this is step 2. I did simplify. Should notice here that the graph actually does look like what we think, or hopefully what we should think. At 0, you can't do anything, but on the right side, it's always the constant function 1. And on the left side, it's always the constant function -1. So that's the graph. So you can see that the right side is going to 1, the left side is going to -1. They don't agree at 0. So yeah. Sorry, is that the limit as x approaches 0 from the right side of absolute value of x over x is 1. And the limit as x approaches 0 from the left side of absolute value over x is -1. Because the absolute value of x will switch on either side of 0. And we know that because we know the definition. So this limit does not exist. There's going to come a point where this limit is going to come up again. So remember it. Remember the fact that absolute value of x over x as x approaches 0 does not exist. But yeah, we can actually show that it does not exist here. Arctangent of x, right? This is like AKA tangent inverse. What do we do here? Can't plug in. How do you simplify arctangent of x? Like, what does it even mean anyway? Like the inverse of the tangent function. Is there a special technique for this? Like, I don't know. Like table of values, like how am I going to figure out the table of values for the arctangent? So here's the thing though. Jhevon expects you to know the graph of arctangent. It's going to come up. And the graph looks like the following. It has asymptotes. So there's an upper asymptote, and then there's a lower one as well. Does anyone remember what the asymptotes are, at least? Where they happen?
Positive and negative 1.
No, not exactly. No. You want to flip the x and y coordinates, I think. Positive and negative 1, I don't think would work either way. It's going to be larger than 1. So remember how you created the arctangent function. You pretty much ignore everything outside of a certain window, and then you reflect the rest of the middle part over the line y equals x. So that first window where you had the asymptote, do you remember what those asymptotes were? Where is the tangent not defined? Like the smallest positive value and the largest negative value for which it's not defined. When is tangent of x undefined?
Is that pi?
It's not at pi, no. Tangent is sine x, tangent x is sine x over cosine x, right? Cosine of pi is that actually exists, that's -1. So you're not going to like divide by 0 or anything. Tangent of pi is in fact 0 because you have sine of pi over cosine of pi. Tangent is going to be undefined whenever your cosine hits 0. Where is cosine 0?
Pi over 2.
It's at pi over 2. The upper limit is pi over 2. And because cosine is an even function, we know that cosine of x is equal to cosine of negative x. So down here, it's minus pi over 2. And the graph looks like the tangent graph, how it was like a curvy like this, and you just flip it. So it's like an S. It's going to look like that. So now, knowing the arctangent graph, answering that question should be not bad now. Well, what's the limit as x approaches negative infinity?
Negative pi over 2.
Negative pi over 2. It's kind of something that you can just know now. Like the limit as x approaches infinity is going to be positive pi over 2. Limit as x approaches negative infinity, be negative pi over 2. You should also know that the limit as x approaches 1 is going to be pi over 4, because sine of pi over 4 and cosine of pi over 4 are the same value. The tangent would output 1, therefore the arctangent of 1 would output pi over 4. Yeah. I have some more examples, but for now we're going to take a break. I will give you guys like 10 minutes to rush everything off, and we will return. So let me stop the recording and we can just chillax for a bit. So 10 minutes.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
We are back. So something like our tangent is something that you would kind of use the graph for. Like that's something where even like a table of values, like you wouldn't really be able to do unless you're plugging in some very large values that are multiples of pi over 4, and it's too much to think about. It's actually a lot easier to get that from the graph. Now let's continue. Moving on to guys like this. All right, so again, it's a random limit. We go through that limit strategy. First, try to plug in. Can we plug in x equals 0? Get 1 minus 1 in the denominator. No bueno. So now you think, well, can I simplify to plug in? Well, can I simplify to plug in? Please throw that question out to you guys. Do you know how to simplify something like this? Can it be simplified? Wouldn't really want to know the graph of this guy. No. Can we simplify? Maybe it's a special technique that we need here or something else. I mean, technically, you could do a table of values, but you wouldn't want to, obviously. Can we simplify?
I don't remember what it's called. I just remembered. Okay. Conjugate. Do you multiply it by the conjugate?
Yes, you multiply and divide by the conjugate. So what is the conjugate in this case?
Oh.
The conjugate of the denominator, right? So
is it square root of 1 minus 3x?
Yeah, so you're going to multiply and divide by the conjugate. That way you're multiplying and dividing by 1. And what is the conjugate here? The conjugate is actually 1 plus 3x. 1 plus 3x plus 1. And so that's the conjugate. Why is that the conjugate? Well, remember the point of the conjugate is for us to take advantage of formulas like the difference of squares. Here, if I think of the radical as a and the one as b, then if I take a minus b times a plus b, that would invoke, right? So that would create a squared minus b squared. It allows me to square the radical in place, right? So I can actually do this to get rid of the radical, which hopefully will make things a little nicer. So that's why I multiply and divide by the conjugate. And the conjugate, when you have a radical, like things to the half power, would be you just change the middle sign because it invokes difference of squares. If you had like a cube root, it's much more complicated, but I don't think we need that at any point. So yeah, multiply and divide by the conjugate. So that becomes, and just knowing what the conjugate does, you can simplify the denominator very quickly. Let me put this on the next line. You'll know that the denominator is just going to become the first guy squared minus the last guy squared. So the radical of 1 plus 3x squared is just, well, 1 plus 3x. Minus the last guy squared, which is 1 squared, so that's 1. So that's what the denominator is. The numerator is going to be, well, x times 1 plus 3x plus 1. All right, does that actually help? Well, let's see what we can do here. This is x times over, well, 1 minus 1. So that's just 3x. And now, hey, there's a multiplication here, so I can cancel those guys. And so now I just have the radical of 1 plus 3x plus 1 all over 3. And now can I plug in? Yeah, there's nothing wrong with plugging in x equals 0 here. I would have radical of 1 plus 1 on the top, which is just 1 plus 1, which is 2. And the denominator is a constant 3. So that's actually 2/3. Interesting. So this is what I mean by, you know, your algebra and your pre-cal skills is going to come into play, because when you're thinking, okay, step 1 didn't work, would step 2 work? I'm expecting you to remember, oh, there's this thing called a conjugate that I can use to simplify this thing, right? And you're going to need to know that such a thing exists. You're going to need to know what it is. And then you're also going to need to be able to actually multiply and do the calculations and actually figure out how to do it. So this is where the algebra skills would come into play. So yeah, you should know that you can simplify something like this by multiplying and divided by a conjugate. If you want to get rid of radicals and stuff to kind of get your x out of a radical prison, conjugates are useful for that reason. Okay, so that's that one. This one, actually very similar to the absolute value of x over x thing that we did last time, so I'm probably not going to really dwell on this. So I'm going to realize, well, this is going to be the limit as x approaches 1 of x squared, 1 over x minus 1, if my x is larger than 1. And it's going to be the limit as x approaches 1 of x squared over 1 over minus x minus 1, if my x is less than 1. Because the absolute value, it's going to give you the value if the thing is positive. X minus 1 is going to be positive as long as x is larger than 1. X minus 1 is going to be negative as long as x is less than 1. So it breaks into those two things, which individually I can simplify. So in the top, it's be x minus 1 times x plus 1 over x minus 1. And in the bottom, it's be x minus 1 or times x plus 1 over negative of x minus 1. Oh, look at that monstrosity. And so that's going to simplify. It's going to simplify. So this will be limit as x approaches 1 of x plus 1 and limit as x approaches 1 of, well, minus x plus 1. So at this point, you can plug in x equals 1. You're going to get 2 as the answer. If you're on the right side of 1, you would get minus 2 as the answer if you're on the left side of 1. So does not exist. If instead, for example, if I had wrote a little plus sign here, then that would have given us 2 as the answer. Whereas if I wrote a little negative sign, it would give us minus 2 as the answer. Maybe I should write that down just as a side note by the above. If I said I was approaching 1 from the right side of x squared minus 1 over the absolute value of x minus 1, the answer would be 2. If I had wrote that'd be minus 2. Okay, so that's that one right there. See it at a glance. All right, so yeah, moving on. Now these guys are going to be interesting. Like, they're crazy, right? Look at how crazy these polynomials here are. So notice here that we have a polynomial divided by a polynomial. We have x approaching infinity, which means plugging in is never going to be an option. But I wouldn't want to graph this. I also wouldn't want to do a table of values for this. So it turns out that there is a trick that you can do in situations like this. And so I don't know if it's like a trick, but here's the trick. Divide each term by the highest power of x, as in, i.e. x to the n, x largest, in the denominator. Pretty much always in the denominator. So you're always going to do you're never going to do this for the numerator. Always the denominator, right? So you're going to just divide by the highest power of x in the denominator. So if you have something like this guy, if you have something like this guy, what you're going to do is you're going to identify the highest power in the denominator. Clearly, you see that that is x to the 5th here. And you're pretty much going to divide every term by that. You're essentially multiplying by 1 by doing this, because if you divide the numerator by x to the 5th and you divide everybody in the denominator by x to the 5th, it's kind of like you're multiplying by 1 over x to the 5th over 1 over x to the 5th, which is kind of like multiplying by 1. So it has the algebraic properties of kind of like multiplying and dividing by the conjugate. So that's what we're going to do. And we'll see what happens here. So I'm going to take 15x to the 5th over x to the 5th plus 2x cubed over x to the 5th minus 1 over x to the 5th over 5 over x to the 5th minus 4x over x to the 5th plus x squared over x to the 5th minus 2x to the 5th over x to the 5th. And things are going to clean up here. That's going to be 15 plus 2 over x squared minus 1 over x to the 5th over 5 over x to the 5th minus 4 over, what's going on here? Minus 4 over x to the 4th plus 1 over x cubed minus 2. Now it turns out that limits have these nice properties, which I'll tell you about the properties of limits afterwards. But it turns out that limits can distribute themselves across the numerator and the denominator of a fraction, as long as you have finite answers when doing so, or as long as the limit exists when doing so. So it turns out we can kind of distribute this limit and just take the limit of each of these terms. And we'd see what would happen. Now, the limit of 15, well, that's just 15. But what would happen to 2 over x squared as x goes to infinity? What happens to 2 over x squared as x goes to infinity?
It reaches 0.
It approaches 0. Multitude of ways you can do that. 0-degree polynomial over a 2nd-degree polynomial, the behavior of the functions will tell you to approach is 0. It's bottom heavy. You also could know that from the graph of 1 over x squared, that it will get to 0 as you go to infinity. But for very similar reasoning, this guy would go to 0. That guy would go to 0. That guy would go to 0. Everybody gets a 0. Not everyone, though. There are 2 people who are left over here that don't go to 0. You'll notice that, so this is 15 plus 0 minus 0 over 0 minus 0 plus 0 minus 2. It turns out that that actually gives us the answer, believe it or not. Because we simplified it into a situation where we can see term by term what's happening with the limit. And so, yeah, it's a nice little trick. So yeah, that's minus 15 over 2 by doing that little trick, dividing by the highest power of x in the denominator.
For that question, why can't we do the top heavy method?
Because it's not top heavy. If it's top heavy, it would go off to infinity. So it's not top heavy here. But this one, you could actually think of the top heavy thing, which we're going to get to that. But it turns out that a similar trick could happen here. Same trick. I'm going to divide each term by the highest power in the denominator, which is, in this case, x cubed. So I'm going to get radical 2 over x cubed. I'm going to get 1 over x squared. I'm going to get x to the 4th over 4 over x cubed minus 13 over x squared minus 2. And then I'm going to notice that, hey, this guy is going to go to 0. That guy's going to go to 0. This guy's going to go to 0. That guy's going to go to 0. And so I kind of end up with something that looks like this. X to the 4th divided by minus 2. And as x goes to negative infinity there, you'll notice that x to the 4th is going to make it positive, but it's going to be a huge positive number because your x is getting going off to negative infinity. And then you're going to divide that by negative 2. So you have a huge number divided by negative 2. You get a negative huge number, right? So we don't really know what that number is. Not really a number because we're going off to infinity. But at the end of the day, that's just going to be a huge negative number. So by doing that algebraic trick, and this is the kind of trick that justifies what I said earlier with the top heavy and bottom heavy with the polynomials. But this guy, the reason why I could use that to help me here is because I can always just divide through by the larger one, and then everyone else is going to go off to 0, and everyone that's inconsequential is going to go off to 0. And then only the guys that are the guys that are actually affecting things will stick around. And so you can make a conclusion from that. But here, these examples, I'm kind of actually trying to get you into thinking about what are the kinds of conclusions you can make. It turns out that there are not as many possibilities as you might think. And I'm just actually illustrating all those possibilities. So here, the largest power of x is on top, and it goes off to an infinite answer. So let's look at the other one here. And again, same trick. Find the largest power of x in the denominator, it's x to the 7th. We're going to divide everyone by x to the 7th. So that's going to look like the limit. So this goes to infinity of 2 over x to the 7 plus 3 over the x would cancel, x to the 6 minus 2 over x cubed over x to the 7 over x to the 7 minus 2 over x cubed minus 3 over x to the 5th plus pi over x to the 7th equal. Now we're going to do the same game. That guy's going to go up to 0. That guy's going to go up to 0. That guy's going to go up to 0. This guy's going to go up to 0. This guy's going to go up to 0. This guy's going to go up to 0. Notice that what you end up with here is the limit as x approaches infinity of 0 divided by 1, which, well, that's 0. So 0 is the answer here. And that's bottom heavy. So it turns out that these 3 examples actually illustrate all possibilities for this particular scenario, which allows me to introduce a special technique. So that's what I'm going to be doing. Okay, so here's the first special technique that you can know about. And it works in this kind of scenario that we had in these last 3 examples. It turns out I don't even have to go through all these calculations. It turns out that there are only 3 things that could happen here. So this technique works for limits at infinity, which means the x value is going to infinity or negative infinity of rational functions. And recall what a rational function means. Rational function means a function of the form y equals p of x divided by q of x, where p, q are polynomials. Q not equal to 0. Yeah, so that's a rational function, which is what we had here. You'll notice that these guys were ratios of polynomials. That's a ratio of a polynomial. That's a ratio of a polynomial. And so that leads us to this sort of situation. Whenever you're looking at something like this, the limit as x approaches plus or minus infinity, it actually doesn't matter, of something that looks like p of x divided by q of x, PQ are polynomials, Q not equal to 0. It turns out that there are only 3 things that can happen in a situation like this. Only 3 things. One possibility is 0 will be the answer, specifically the number 0. And this happens if the degree of Q is greater than the degree of P. Maybe I should actually remind you about that as well. Recall the degree of a polynomial p of x written degree of p is the highest power of x that appears. So you're pretty much going to look at the highest powers of x, essentially. And if the highest power of x in the denominator is larger than the highest power of x in the numerator, the answer will be 0. It'll always be 0. And this you can say is bottom heavy. So I can give you a limit like this one, and you'll just tell me, oh, the answer is 0 because it's bottom heavy. And that's showing your work. I don't expect you to actually do this all the time. However, I do show you that because I'm sort of weird in that sense. There are instructors and there are contexts in which whoever is grading you or looking at what you're doing would expect you to show this. So I'm showing you that just in case you're ever in that scenario, but Jhevon doesn't care. Like, I don't care if you show this or not. You can just tell me the answer is 0, and showing your work means you would just tell me, oh, it's bottom heavy. And that would indicate to me that you realize, oh, the highest power in the denominator is larger than the highest power in the numerator. I'm going to assume that you know all that because if it's not bottom heavy and you say it's bottom heavy, then I'm going to know you don't really know what you're talking about. And if the answer is not 0 and you say it's 0, then I would actually know. So you would just say bottom heavy. That's your answer. A second scenario would be you would get an infinite answer. So you can get a plus or minus infinity. This will happen if the degree of P is larger than the degree of Q. So that's what happened up here. So notice that your P is this guy. The largest power of x is x to the 7th, right? And your Q is this guy. The largest power is 3. 7 is bigger than 3. So the top has a larger power than the bottom. So it has a larger degree than the bottom, which means it's top heavy. Like most of the weight is in the top. And that tells you that you're going to go up to infinity. I will preface here that you need to pay attention to the signs. Because whether it's positive or negative infinity would actually depend on the actual terms. The fact that this was a 4th power tells me that if I plug in a negative infinity, it's going to turn positive, and then the denominator is negative. So what this is like a positive number divided by a negative number. So I know that gives me a negative number, but it's going to be a negative infinite. No, it's going to be negative infinity, right? But I'm watching the signs. So it's possible that I could get a positive infinity as a result, but you just pay attention to the sign. Okay, the denominator is going to be positive while the numerator is also positive, so it's positive infinity. Or the denominator is going to be negative and the numerator is positive, so it's going to be negative infinity. Or the denominator is going to be negative and the numerator is going to be negative, so it's positive infinity, right? It's going to depend on the signs of the biggest terms. So watch the signs of the they're called leading terms. Leading in the sense that they are attached to the x with the highest power, not necessarily in the sense that they're the first guy to appear. Like leading doesn't talk about how they appear in line from left to right. Pay attention to the signs of the leading terms. And here you would say it's top heavy. Right, and that's showing your work. So that's the second scenario. Now, of course, it's possible to not have 0 infinity as the answer. That was in one of these examples right here. We got minus 15/2. Where did that come from? Well, that's the third scenario. And you'll notice here that if I examine the highest powers in the top and the bottom, it was actually the same thing. So when I divided by x to the 5th, I got a constant in the top and a constant in the bottom, and everyone else is going off to 0. Turns out something like that will always happen when the highest power is the same in the top and bottom. So it goes to the following. It will go to, the result will be the leading coefficient of P divided by the leading coefficient of Q. Right, so what is the leading coefficient? Call the leading coefficient of a polynomial is the coefficient of x to the highest power. Or it's the coefficient of the highest power of x, you can say. So if you look here, when the powers were the same, essentially what the answer turned out to be was the coefficient of the leading term here divided by the coefficient of the leading term there. And that's where the 15 over minus 2 came from, the minus 15 over 2. It turns out that that's always going to happen when the highest power is the same in the top and bottom. So this happens in the only other scenario that is left off, and that is if the degree of P is equal to the degree of Q. And in this case, you can show your work by telling me that what I'm applying is a ratio of leading coefficients. Right. So that is a special technique. You can actually use a similar technique more generally, but the idea is you always want to divide by the biggest, baddest function around. So if there happened to have been an exponential function in the denominator, I would divide everyone by the exponential function, right? And that's what you can kind of see to figure out the relationship I gave you guys above. By just doing that trick with algebra, where I'm multiplying and dividing by the same thing, you can figure out that an exponential will beat a polynomial, blah, blah, blah. Yeah. So what we're going to do now is we're going to do, fix these. Is we're going to do a bunch more examples, but now we're going to do them essentially rapid fire. We're going to do them very quickly because we now have a special technique under our belts. So here's another example. Okay, so we have a bunch of examples here, A, B, C, D, F, G, H, but they all fall under this category. So even more examples, but wait, there's more. Okay, so just gonna pretty much ask you guys, what's the answer here? Chime in and tell me what you think. If you understand the strategy I mentioned, you should be very quick at this. So let me do it here. I guess you guys can take a picture or something, or just have the notes up in another window so you can see this, and then you can answer. Because the idea is, you see limits like this, it should take you like 3 seconds or less to know what the answer is. Shouldn't take you a long time at all. The only one that might take you up to 3 seconds is the middle one, where you have to like pay careful attention to the signs. That'll take a few seconds, maybe 5 seconds, right? But you should not be taking longer than 5 seconds to do any of these, or to actually know what the answer is. Maybe if you write slow, it'll take more than 5 seconds to write it down, but it shouldn't take a long time for you to know what the answer is. Okay, so what's the answer here?
0.
0. Why bottom heavy? Done. That's the answer. And that's showing your work. It's bottom heavy. The highest power, you only focus on the highest powers. The highest power is on the bottom. It's bottom heavy. 0 is the answer, right? That's from step 1. Well, the first part in this piecewise thing. What about here? What's the answer? Is it going to be 0? Is it going to be something else? Like, what is it? What are you focused on, by the way? Maybe I should ask that. What are you looking, when you see this, what do you notice? What are you paying attention to? Because I look at this and the first thing I would notice is, well, this guy. Because the strategy does apply to limits at infinity. I probably should like double highlight that, because that is something that students mess up all the time. Sometimes they try to apply this trick in a situation where it doesn't apply. Like your x is approaching 1 and they're like, oh, it's ratio of leading coefficients. Like it doesn't work in that situation. Like you can't do that. So that's the first thing I would notice. So once I notice it's a limit at infinity, and I'm like, hey, these are two polynomials, one dividing the other. So the second thing I would notice is, what are the highest powers? I would literally ignore everyone else. The other people don't matter. Like they're not the ones making the decision. The biggest powers are the guys driving the bus. They decide where you're going to go. So now you're going to notice who's the bigger one. So here, the larger one is in the top, which tells you right away it's top heavy, which tells you right away it has to be infinite. Now the question is, which infinity, right? So now you're going to worry about, well, which infinity is it? And so you are going to do that. So now you're going to worry about, well, which infinity is it? Well, I'm going to negative infinity, right? So I'm going to have like negative infinity cubed divided by negative infinity squared, right? So that is, which it doesn't even make sense to write that, but I don't care about, we're not at infinity. So we're just thinking of infinity here as a huge number, bigger number than anyone can imagine, all right? So if that number is negative and I cube it, what happens? Well, it stays negative. All right, well, if that number is negative and I square it, what happens? Well, it becomes positive, but then the coefficient is negative, so it stays negative. What happens when you take a negative divided by a negative? Well, you get a positive. So the answer is positive infinity. Right. So when it's top heavy, it's a little bit more time because you have to kind of pay attention to the signs. You have a negative x squared. And a positive x cubed. what does that mean for the sign if I'm plugging in a negative number for x, right? That's what you have to think about. And if you ignore everyone except the biggest terms, they would be positive. It will overall, it will give you a positive calculation. Okay, what about this one? Let me keep pointing this out. So yes, it's a limit at infinity. All right, cool. What is the answer? So we can look at the highest power of x. It's bigger in the top. So I know it's top heavy. So I already know me showing my work is pretty much me writing down the phrase top heavy. Okay. So top heavy means it's going to be an infinite answer. I just need to figure out what sign. So I know it's going to be plus or minus infinity. Then I go to the signs. So this is a -2 times something to the 5th over a 3 times something to the 4th. What is that thing? Negative infinity. So negative infinity raised to the 5th power, it stays negative because it's an odd power, times a -2, that's a positive. Negative infinity raised to the 4th becomes positive, right? So that's also a positive. So that's just a positive number. So again, positive infinity. Okay, what's this one? Is it top heavy or bottom heavy, or what do you think?
Would it be,
Go ahead.
sorry, sure, would it be -1/3 because you can plug in negative?
Can plug in, yeah. I was seeing who's paying attention. It doesn't apply the strategy that we've been talking about. This is strategy 1, step 1, you plug in. So on top, that's -2 over 6. Yeah, so it was neither. It was none of those. Just trying to see if, I've been circling the infinity in a red circle this whole time. Just want to see if you guys are paying attention to the fact that it only works for limits at infinity, right? So this strategy does not work in general, right? Because if you try to apply that strategy here, you would get the answer 1. So, which, I mean, I'd actually bet money on the fact that if I'm giving a test to like 20 students, like someone's going to get the answer 1 and tell me that, oh, it's ratio of leading coefficients. They're going to get the answer -1. I'm like, nope, because it's going to -4, not to infinity or negative infinity. So yeah, this was step 1. So it's not, this one going to infinity again. Notice the highest powers. Notice that x is a positive number. It's going to positive infinity. So Clearly that's going to negative infinity because it's top heavy. This one, I notice it's a limit at infinity. So I look for the highest powers. Highest powers are the same. It's both x to the fourth. So it's going to go to -7/2 because of ratio of leading coefficients. This one, notice it's a limit going to infinity. So I look for the highest powers. All the other guys don't matter. And so, by the way, remember E is a constant. It's not an exponential function. That's just a constant. So you're not going to think like the E is going to like mess things up because it's just a number. Well, circling doesn't agree. The top one is bigger, so I know it's going to go to infinity. It's going to be top heavy. Which infinity though? Well, x to the 13th is going to be negative because I'm plugging negative infinity times a negative. It's positive, so it's positive on top and positive on the bottom. Yeah. This one, limit at infinity. Find the biggest guys. Answer here is 7/4. Ratio of leading coefficients. Do we have any more? No. So that's one special technique. This special technique works in this particular situation. If you're taking the limit at infinity of rational functions, there's a standard technique. There are only 3 types of answers. It's going to be 0, it's going to be infinite, either plus or minus, just pay attention to the signs, or it's going to be the ratio of the leading coefficients. And yeah, you can find the limits by doing one of these strategies if you know you're in this situation. So that would be like your step 3. This will be one option under step 3 of the limit strategy. Right, so if you try to plug in, can't work, try to simplify, you can plug in, can't work, and then you're like, is it a limit at infinity of a rational function? Then you automatically know it's only one of 3 answers, and you can easily know which by just paying attention to the highest power. You get to the answer very quickly, right? You don't have to need to know what the graph is or plugging any values or any of that. You can just know, in this situation, I'm allowed to use this technique. One of 3 possibilities, and you should be able to tell which. Here's another technique. And it's called the Squeeze Theorem. So there's a nice little theorem called the Squeeze Theorem. And it's essentially a theorem that tells us we can determine the answer of something by squeezing it between 2 other things, where those 2 other things actually approach the same thing. So here's what the Squeeze Theorem says. So theorem, it's called the Squeeze Theorem. Very rarely you might hear people call it like the sandwich theorem because you're sandwiching between 2 things, but I think Squeeze Theorem is far more common. Yeah, so here's what the theorem says. Suppose that near x equals a, the following is true. You have functions that line up this way. F of x is less than or equal to g of x is less than or equal to, say, h of x. Right, so you know that when you're close to this value, your functions stack in this way, right? The output of h is always going to be larger than the output of g, and that's always going to be larger than the output of f, right? And if you look at the limit as x approaches a of the f equals some value L, and the limit as x approaches a of the h equals some value, it's actually the same value L, then it turns out that the limit of the middle guy must be L, right? So if you know about the two guys on the ends, and you know that in fact they go to the same number, then that is enough information to tell you what the middle limit is going to. So now, why does this work? Well, the idea is if f of x is less than or equal to g of x for all x near a, then the limits would obey the same inequality. Limits maintain inequalities, right? And hopefully this is clear, because remember what the limit is. The limit is tracking the y value. It's tracking what the outputs are doing. But we're told that the outputs of g are always bigger than the outputs of f in this scenario, which means that the limit of g must be larger than or equal to the limit of f, because the limit is only tracking the outputs anyway. So the output of the g must be larger than the output of the f. And so if I'm tracking what they're getting close to, whatever they're getting close to, the g is going to give you something bigger than the f, right? Potentially equal to, but bigger than or equal to. If it's a strict inequality, it's a strict inequality. Limits maintain inequalities. And by the, this is like a theorem. This isn't just something that we just, I mean, it's very intuitive, but it was something that had to be proven. It's another theorem. And so, i.e., limits maintain inequalities. And so, if we had, f of x less than or equal to g of x less than or equal to h of x, what that means is I know that the limits must line up the same way. And if we assume that this guy is equal to L, and this guy is equal to L, and we have the limit of g stuck in between, now you ask yourself, what are the possible values that this limit could be? It has to be greater than or equal to L, and at exactly the same time, it has to be less than or equal to L. Well, you can't be greater than a number and less than a number at the same time, so the equality must take effect. It must be equal to L itself. If you're squeezed between 3 and 3, you have to also be 3, because there's nothing in between 3 and 3, right? So this is what's called the squeeze theorem. So your limit of g must be L, because what else is it going to be? It can't be anything else, right? It's squeezed between the same number. And so that's the squeeze theorem. So The squeeze theorem is a general technique. But it usually comes in handy for trig functions. For limits of trig functions. In Calc 1, right? So all the things I say, it only applies to Calc 1, it doesn't apply anywhere else. So most of the time, the vast majority of the time, 99.99% of the time, if you're applying squeeze theorem in Calc 1, you're doing it on the limit of trig functions, okay? It's not the only thing that you would do on the limit of trig functions, but it happens to be a very nice thing to do with trig functions. And this is because with trig functions, you can get a triple inequality with certain functions very easily, because we get some triple inequalities for free. With trig functions. Example, if I say sine of x, it turns out that I automatically will know two things on either side of sine of x. If you know about sine of x, which I'd expect you to know because it's a trig function and you guys are expected to know trig, you'll know that it always is greater than or equal to -1 and less than or equal to 1. So I know that that's true always, right? So along with the sine function, there's a triple inequality that's always in the background. Similarly for cosine. Right? That's always true. We saw with the arctangent. That's always between these guys. Right? There's a lot of trig functions and inverse trig functions where it's like we know just by knowing that that function is involved, I can automatically put something on both sides of that thing. I can know that, for example, if I were to square the sine function, then of course that would be bounded here, right? Because you won't have the negative side anymore. But the idea is if these trig functions show up, I automatically know that, oh, I can put something on either side. So I can kind of get that for free. And so that comes in handy with some nice examples here. So let me here are some trig examples. So you see something like this. Limit as x approaches infinity of sine x over x. And that is probably a little bit strange. What would that mean for x to go off to infinity of this guy? So one thing you can do, now it's the problem with the sine function in general, or like a cosine function or a lot of trig functions, is that they oscillate, right? So it's hard to get a y value to settle anywhere to get an answer. So the squeeze theorem can often help us around that. So here you can just say, well, we know that my sine of x is always between 1 and -1. So that would mean that if I divide by x everywhere, that will happen, right? Because since x positive as x is going off to infinity, right? When you divide by a positive numbers on an inequality, the inequality stays the same. So now I have three functions that are in line, like my f, g, and h from the squeeze theorem. So that tells you that, hey, I can hit all of these guys with the same limit. So that must be true, right? So out of nowhere, I could create this triple inequality of limits because there's a sine function involved. And for the sine function, hey, you can always assume that sine is between -1 and 1 all the time. It will never be not that, right? So you can make that assumption at any point in time, right? And by doing that, I can get this triple inequality. And now the magic happens, right? So of course, based on what we know, this is 0. And this is also 0. So we have that the limit of sine x over x as x approaches infinity is greater than or equal to 0 and less than or equal to 0. So what is it? Has to be 0. Then you say by squeeze theorem. Sometimes I'd write it like that. So that's the squeeze theorem. So you get sine x over x is that. You do a similar thing here. You can't really have x approaching 2 creates a situation in the cosine where you're dividing by 0, no bueno. So, however, we know that if x is not 2, which for the limit we don't have to assume it's 2, this thing is between 1 and -1, whatever the output is. As long as the angle is defined, which it's defined as long as x is not 2, that's true. Which means that's true. Maybe I'll make this a fourth. It's true for the cube as well, but it's I don't want to have to worry about, well, what if slightly less than 2? You have to turn the inequality signs around. It's going to be the same thing. The answer is going to be 0 anyway, so whether it's positive or negative, it doesn't matter. But just to like not have any doubts. So that's true. The cosine is bounded by that as long as it's defined. I can multiply all sides by x minus 2 to the 4th. Then if I hit it with a limit, it's going to maintain the inequality. This guy goes to 0. That guy goes to 0. So the answer is 0. That's that. See that monstrosity of a limit? Try to plug in. You can't. Try to simplify your plugin. You can't. It's not a ratio of polynomials, so we can't do that super cool special technique. I don't know what the graph of that looks like. I don't want to plug in a table of values for that. That's crazy. However, there's a trig function. One of the things that often work with trig functions is the squeeze theorem, because we're in Calc 1. So that's where you would think, okay, squeeze theorem. I can bound the cosines, see what happens, and you would actually get away with it here. Similarly here, you can't really plug in x equals 0 because of the division by 0 problem here. However, we know that if x is not 0, the output of this function is going to be between -1 and 1, which means I can multiply by x squared on all sides, which means I can hit it with a limit, and the inequality stays the same way on all sides. And yeah, that obviously goes to 0. Obviously goes to 0. So you have that. Now the answer isn't always 0 for a squeeze theorem problem, but the nice examples that I could get you there are all 0. So that's another special technique, squeeze theorem. I'm going to tell you about a third one, but we're not going to do any examples because we're essentially out of time. But it also applies to trig. There are a bunch of limits called the special trig limits. They're so special. So the following limits are true. It turns out that if you take the limit as x approaches 0 of sine x over x, the answer is actually going to be 1. Take the limit as x approaches 0 of tangent x over x, the answer is also 1. Turns out if you take the limit as x approaches 0 of 1 minus cosine x over x, the answer is 0. So these are the special trig limits. Because these are 1, the reciprocal also works. This one you can't take the reciprocal, but because it's 0, you can take the negative. So it's also true that if I had the cosine of x minus 1 over x, that would also be 0. One other thing I would say to note is that it's actually important that the angle is the same as the guy on the top. That's not a coincidence. It can actually matter if these two are not the same. Right? So these I'm not going to prove for you. You can prove them using geometry and some trig identities. But these are just given. These are things we know now. Like, memorize these. Now, once you have them memorized, that gives you the ability to do a whole bunch of other kinds of examples. Which I'm going to paste them here. There we go. Try these for next time, which is Monday. Turns out with these guys that I gave you above and a little bit of knowledge of algebra and pre-calculus, you can actually find all of these limits. So they're not really ones that Squeeze Theorem would help you with, but they will, knowing these guys can help you with these. So that's another technique. So Squeeze Theorem, general technique, but it's usually very useful when it comes to trig functions. And of course, knowing these only applies to trig functions, right? It applies to these limits are very specific limits that you should know by heart. So when it comes to trig limits, these are two things that are very important for you to know: the Squeeze Theorem and the special trig limits. So I will leave you with that. We'll knock those guys out the way next time, and then I'll tell you about, well, long overdue to tell you about some properties of limits, the algebraic properties, and then I think we're going to move on to a whole different topic, which is continuity, where I'm going to tell you about continuous functions that were mentioned earlier. But we'll stop there for now. So thank you for your time and attention. I realized that, you know, as a class, I think the limit is like 90 minutes. Like before the break, you know, a lot of people are answering. Like after the break, I asked a question. I was like, I hardly know my name now, Jhevon. Like, so it's like the first half of the class, participation. Second half of the class, I should just lecture to myself. You guys will catch up later, I'm sure. So I'm not gonna ask as many questions, because by that time, it's like, dude, it's like 9 p.m. and we're like 2 hours into a math, like it's too much. Like I just want to curl up in a ball right now. But yeah, do those for next time. As you guys know, the notes are at the link that you can find at class webpage and all that. And yeah, that is it. So thank you for your time and attention. Enjoy the rest of your night. Nothing else to say, I think. So yeah, I will catch you guys in the next one. Ciao.